Welcome to the Astrophysics Podcast. So, we've talked a lot about black holes on this podcast. Given that they represent powerful distortions in the fabric of space-time, you might think that black holes would be the most mysterious objects in astrophysics. But I'm not so sure. Actually, from one perspective, black holes are quite simple. They can be straightforwardly described as known mathematical solutions to Einstein's equations describing how space and time work. On the other hand, there are some objects that are so extreme, we don't even know what equations to use to describe them. That is the case for another type of astrophysical object that we call a neutron star. Neutron stars are the most compact, dense objects that can exist in the universe, aside from black holes. You take a star about 1 to 2 times the mass of our sun and compress it into an object around 10 kilometers in radius. That gives you a star with approximately the density of an atomic nucleus. At those densities, we don't really know what happens because we can't even come close to reproducing those conditions in a laboratory on Earth. So these super dense stars are a great way to test out fundamental physics. In addition to being a complex mess at their core, neutron stars can also possess some of the strongest magnetic fields in the universe, which is often what enables us to detect them here on Earth. Neutron stars are dense, messy, complicated objects, and we don't even really know what equations describe them. So, what kinds of interesting things can they do? For answers to that question, we can talk to Dr. Wen-Fai Fong, who is a professor of physics and astronomy at Northwestern University. Dr. Fong is an astronomer who studies all kinds of things that neutron stars can do, from emitting bright flashes of radiation to producing strong gravitational ripples in the fabric of space-time. I'm Paul Duffel, and this is the Astrophysics Podcast. I'm trying to figure out if there's anything else I needed to tell you. Yeah, I don't think so.
We'll wing it. You can edit it out.
That's right. I'll edit out all the things where we're not smart. So, good. Okay, you ready?
Yeah.
Okay, Here we go. Welcome to the Astrophysics Podcast. I'm Paul Duffel, and my guest today is Dr. Wen-Fai Fong, who is a professor of physics and astronomy at Northwestern University. Dr. Fong, thank you for joining me on my little podcast.
Thanks for having me, Paul.
You're welcome. So now I'm trying to remember. I was trying to remember this morning, like how long? Because I was actually looking up your information, and
okay.
I was like, I realized we got our PhDs the same year.
Oh yeah, 2014.
And, yes.
Yes.
And I was like, and I was trying to think about when I first met you or first encountered you.
Yeah. I actually don't remember. I mean, I knew that you were Andrew McFadden's student and up and coming superstar. But I think it took a long time for us to meet. Anyway. Maybe when you came to visit Northwestern.
I'm sure we probably met
in passing in conferences. But I knew of your work for a long time before I met you.
Nice.
Yeah.
Well, I remembered your work. I remembered reading, when I was at Berkeley, I was reading a paper on gamma ray burst opening angles of short GRBs.
Yes.
I thought it was very cool.
Yeah.
So I remember I was paying attention to your work too. It wasn't just
I know. It's funny how that happens in astronomy. You kind of just know of people and they're like phantoms, and then
my students actually
meet the real person.
Yeah. My students were telling me, and I remember this too, is when they were always surprised when they meet somebody, like they see somebody's written all these papers, and they meet them and they're young.
Yeah, that's right. I know.
You always assume they're going to be some really old.
Well, the young people are writing the most papers generally. I remember when I first met Brian Metzger, that was the same too. At a coffee break, I was like, "Oh wow, you're a postdoc." So yeah.
Yes. So anyway, it was funny because I'd forgotten that I had that feeling too. But my students say. Yeah. So then we're going to talk about you and where you grew up and all that stuff. So let me start by asking, where did you grow up?
I grew up in Rochester, New York. The skies are super cloudy, but occasionally they have stars that show themselves. Yeah.
And so what was that like?
Yeah, it was great. It was a great place to grow up. It was, I mean, I have my kind of very kitschy how I got into astronomy story, where like my 8th grade teacher assigned each person different projects, and mine was like chart the phases of the moon over the month. So I like had to go out in my driveway and be like, cloudy tonight. Okay, go out my driveway again. Oh, it's like this waxing crescent or whatever. And then that, I mean, it's kind of really silly, but it really did force me to like look up. And then I got a little bit more interested and started going to like amateur astronomy club meetings and stuff as a camps and stuff. Yeah.
So that was 8th grade when you had that assignment?
8th grade, yeah.
So you were already getting clouded out by weather conditions.
Yeah. But I didn't have to travel like across the globe to get clouded out. I just had to look up. Yeah.
Okay, that's cool.
Yeah.
And so very early now, did you feel like that was like a moment where you're like, this is really fun and I like doing this, or was it just, I don't know?
Yeah, it would. I mean, I was just like, oh wow, astronomy is really cool. Of course, in 8th grade, you're not really thinking about career.
Right.
And then actually in high school, I applied to this program at the University of Rochester, this pre-college experience in physics for women. And that was really awesome. It was run by 2 graduate students, and it just made me realize, oh my gosh, there's like so many women who are really interested in physics and, you know, really, really good at math. And I'm really excited about using math for applied physics concepts, and then surrounded by other girls who are interested in physics. So that was probably the formative experience where I realized, oh, this could actually be maybe something I like, you know, I'm very excited about pursuing in college.
Wow.
Yeah.
And so, okay.
And that program still exists today at University of Rochester. Yeah.
Oh, that's great.
Yeah.
Well, I'm sure they're happy that they created an astrophysicist.
They've created many different people.
Okay.
Yeah.
They've created many different types of people. Yes, not just astrophysicists.
Yes, that's right.
That's great. So now, this, going back to sort of 8th, was that the first, like, when you were doing this phases of the moon thing in 8th grade, is that the first memory you have of getting excited about science, or do you have other like?
Ooh, I mean, I have like my at-home memories because I mean, in terms of astronomy, yes, but science, I've always been interested. Like my parents got me like a kid chemistry kit when I was like 7, where you get like a bunch of little different vials of who knows what materials. And it's like one of those Smithsonian kits. And you like mix things together and things change different colors or react different ways. Remember, had like little toy goggles and stuff. So I was always really interested in science in some form, but that phase of the moon project kind of turned me onto astronomy. Yeah.
So then, you mentioned your parents. What did they do?
Yeah, so my father is in medicine. He's a geneticist and a pediatrician, and my mom is a manager at Xerox. So not scientists, but very like good with quantitative numbers and yeah.
Well, and if you're, I mean, I would think if you're even if you're not a scientist, if you're a doctor, you're very academically minded.
Yes. Yeah. Exactly. Yes, definitely. But I don't think they expected me to like go into astrophysics because that's kind of a niche career. But always.
I suppose so.
Yeah.
Was there something they were hoping for you, or they were?
No, I mean, so I was very into like organizational things. So I was really into like being a cashier or being like a mail person, things that are like, oh, you get to sort into things, or like I take your money and then I like get to ring the cash register and give you back the precise change. So I was very like into, and they were like, yeah, maybe not those as like long-term careers, but like good, like, but I got to live out those dreams in like high school odd jobs and stuff, but no, nothing in particular. Yeah.
That's cool. So then, okay, so then, and when do you think, when do you feel like you started thinking about astrophysics as kind of a career, or?
I think probably my first year of college. I actually applied to like a bunch of summer programs and didn't really get into anything because they're all really competitive and not really geared towards like first year college students. Like all these REU programs are more geared toward older students. But then I just like cold emailed a bunch of people at the University of Rochester. I went back home for the summer. I was at MIT for college and then went back home, and Eric Blackman, this professor at the University of Rochester, basically took a chance on me and was like, sure, I'll give you some work to do do. And we did like accretion disk physics, like particle and cell simulations of two temperature plasmas and accretion disks. So it's very different from what I do now.
Yeah.
But that I think was the first time I realized, okay, like this was a really easy, really, really fun summer. And like, why not just continue to do it? It wasn't like a conscious decision, like I'm going to do this research experience in this one and this one, and then I'm going to get a PhD. It was more like go with the flow back then. And I really liked the way I spent that summer. And I liked how the astronomy community was fairly small, because he put me in contact with a professor at Harvard, then Julia Lee, who like gave me an opportunity the next summer. So I kind of liked that.
Yeah,
that thing.
I remember that being like sort of go with the flow too. Of like, I like doing this thing that's in front of me right now.
Yeah, exactly. Yeah, I wasn't really. I mean, I wasn't really like a very conscious decision. Yeah.
It's interesting you mentioned. I didn't realize you'd done all this. Like you had done these PIC simulations. It was pretty hardcore theory, right?
I mean, I don't think it was like.
I mean, it was an undergrad project, so I didn't. I wasn't assuming you were like.
I was just like running someone else's code and then like recording the output, but learning a little bit more. Yeah.
But it's still pretty cool.
Yes.
Anyway.
Yeah. Thank you.
But it probably helps in some sense later on when you're as an observer, like knowing a little bit, like just a little bit about what's going on under the hood, because like a lot of people use these simulations to interpret the observations you see. So.
I mean, it's amazing because at the time I didn't know particle and cell simulations were still like I didn't know the landscape of all, but now when I hear it, I'm like, oh, I know a little bit more about that technique because I had this undergrad experience. So
that's cool.
Yeah.
So at what point do you feel like you learned how to be a scientist?
I'm still learning. Probably in those, like really truly when I really had to own my first research project. I'm like, maybe it's kind of late, but like maybe first or second year of PhD maybe. Because every up until then kind of projects are handed to you. You take with it what you will and make it your own. But it's really until I really felt like, oh, I can own this project. I'm putting my creative ideas in, that I feel ownership, which probably wasn't until like second year of PhD. Yeah, I don't know if that's kind of late for.
So I don't think that's too. I mean, this is the point. I mean, I asked this question. Most people answer sometime during their PhD. But because it is, that's the point when you are learning how to be a scientist. So maybe I don't know. It's kind of funny. Like that's one of those
funny.
questions.
I thought it was late.
No, it's not at all. And I think, I mean, what like so, and so you defined being a scientist implicitly in that question is what is a scientist? And so you're sort of defining it in sense in terms of like whether it's your project, like it's a project that you are championing, even if your advisor sort of suggested to you the idea, you're sort of spearheading the research.
I don't really. I felt like I was more like a student, I guess. Then, but I also like. I'm not joking. I feel like I'm still learning the different aspects of how to be a scientist. Like when you go into different techniques, and you have to like learn stuff all over again.
Yes, I mean it's true. You do. I mean it is true. Like so, you're always learning new things. Like I definitely am. There was definitely a period of time where I kept being like, there's another type of supernova that everybody's known about for the past several decades, but I just learned this particular name. So there's lots of things that I know that you're learning. But there is also that aspect of learning the process of like, engaging with the scientific method. Yes.
Actually, you know what? I will say maybe concretely my first observing run when I actually went, my PhD advisor, Ido Berger, took me to the Magellan telescopes in Chile. And I remember that during the end of my first year, beginning of second year, like that summer. And I think he took me and he was like, you're going to learn all this someday. And I was like really fish out of water, like really expensive telescope, every minute counts. And I think that when you're like actually like taking your own photons and seeing them and analyzing the data in real time, that actually maybe was probably one of the most formative experiences for like feeling like, okay, I'm like a scientist now.
You're the one running things.
Yes. Yeah, exactly. And like really learning the scientific method really on the fly.
That's cool.
Yeah.
So good. So now you're an astrophysicist.
Yeah.
What do you like the most about your job?
I would say advising PhD students. And I mean that in the sense of, so I graduated my first 2 students last year in my group.
Congratulations.
Thank you. Yeah, and they're doing great. And I think just there was no, like it's stressful to be feel like you're responsible for a student and their kind of livelihood. You want to make sure they, get a good project and have a good project or that the community receives it well, et cetera. And then, but then to see that culmination and see that transformation, especially on the Defense Day, was really exciting. And I think that was like a super high. And I feel like that's going to keep, every year that I graduate students, that's going to, and then you realize like, oh my gosh, this is the purpose. It's you spend your whole life training yourself.
Yes.
And then now you're training others to do similar things. And that was very meaningful.
I love that too.
Yeah.
I know exactly what you're talking about, that feeling of like, because it is true. Like most of your career, you're there for yourself.
Yes.
And then you transition to become a faculty, and then your job is to help these other people and get started on their careers. And that feeling of like when a student suddenly is like, it feels like it does happen in stair steps where they suddenly are doing things, taking charge of it themselves and doing things way.
I mean, I really like it when I'm just not needed anymore. Sometimes like we have Slack to communicate, and sometimes I'll follow up and be like, oh, okay, remember to do this, and they're already done, and that's those types of things. I like when that happens, when I'm just superfluous. So so I think that, I mean, it's kind of a cliche answer, but I think I realized, oh my gosh, this is my purpose here.
Oh, that's the best. I love that. So is there anything you don't like about your job?
It requires a lot of different learning curves with things I wasn't really trained for. Anything from managing a committee that I've never really been in charge of, to managing your own expectations across many different students. So I feel like they're trained, I wish I'd gotten more training, and it's just a lot. There's a lot of demands on the job. And it's hard to convey that too to younger people. And I actually hate telling my own students I'm too busy this week or something, because I have all this other stuff I have to do. And so I try to really explain this is actually literally what I have on my plate, just so they understand it's not, I'm just putting off your so reading your paper draft for nothing. Yeah.
And they're not feeling they're not allowed to bother you, that sort of thing.
Yeah, exactly.
It's you have a specific thing.
I'm pretty much an open book when it comes to my commitments. But it's that feeling overcommitted and behind. I never really liked that feeling, but I kind of just got used to it. That's one of the aspects I don't love about the job.
It is amazing how we're really not trained on any. I mean, we learn how to do research really well, but we're really not trained about the vast majority of our
even
job
advising PhD students. It's a really big learning curve. Mm-hmm.
They just go, oh, you'll get it.
I know you'll get it through experience. Yeah.
So, what do you think is sort of the most challenging part of getting to where you are in academia?
I think not getting in your head. Yeah, I think it's really it's a very strong mental game. Sometimes I think at almost every stage you're going to compare to yourselves to others, and you're always told, oh, don't compare to others, especially during your PhD. There's no use. I always tell my students there's no use in comparing to this student got out a paper before I did. They're in my same cohort, et cetera. It's not, but that still trying to practice that is challenging, and sometimes can be very debilitating, down to okay, I got one postdoc job, and this other person got 10. Okay, I got a really good job, but what does that say about me and my prospects in the future? So I think that at every step has been
I'm really
tough.
bad at that. I'm also just very bad at taking criticism at any point, or any negative thing. It's I just fixate on.
Yes, exactly.
But it's a similar vein, I guess.
Even today now, if I feel like, oh, I really didn't answer that question well or something, or I should have known that, it's still, but now I'm like, you know, with tenure and stuff, I'm like, well, whatever, I have nothing to lose. But that definitely could have been like debilitating.
I still get emotional when I get like a 4-star review on my podcast. Like, I'm like, why didn't they like it all the way?
Give it 5 stars, listeners.
Everything, I don't know. Somehow I get under like those sorts of like little
you fixate
things
on the
that are so stupid, like I shouldn't care about, but I can't help it.
You fixate on it. But then I got good advice that like no one, like say you answered a question or something, like no one's gonna go like be up at night thinking about that. Like no one's gonna, like they're gonna sleep well at night, whoever asked that question, and they're not even gonna remember it, and you can follow it up with an email or whatever. So I've learned techniques around it. But like not getting in your head every step of the way, because that can definitely be like change a career decision, for instance.
Get into part 2.
Okay.
Where we're going to ask you, basically we'll talk about science.
Okay, great.
So let's start out by, this is how I always ask the first question, which is, when you meet a new graduate student or a fellow scientist and they ask you what you work on, what do you tell them?
I tell them I work on explosions in space.
Okay, and so, by the way, I didn't say this at the beginning, but feel free to say things in a complicated way, but we'll.
Oh yeah, then you can just.
Because we're having a conversation.
Yes.
And it makes me sound good because I'm explaining back.
Yeah, then you sound really smart. Yeah. Great.
So that works really well. Anyway, so when you say explosions in space, that's a pretty general thing.
No. So I tell them I work on 3 main categories. So one is these short gamma ray bursts, where for a long time we didn't know their origins, or the most energetic explosions that we know of. Mm-hmm. And then after many years they were connected to neutron star mergers, the mergers of these 2 dense cores of leftover star stuff that are merging together, and those neutron star mergers can be detected via a whole new way. So traditionally I look at the electromagnetic spectrum and
just to clarify, this is part 1 of what you work on. We're still on.
Sorry. No, it's going into part 2.
Okay.
So part 1 is short gamma ray bursts and their origins and looking at where they come from. Part 2 is now looking at the progenitors, the things that cause short gamma ray bursts, neutron star mergers, but in a different way, via gravitational waves. And chasing those too.
So that's generally about when neutron stars merge with each other, or maybe when a neutron star merges with a black hole. And then it creates a lot of light.
It
creates a lot of light, and it creates a lot of gravitational waves, and you are interested in both of those things.
Right. And then the third thing is fast radio bursts. It's a kind of a similar thing in the sense that they're a really prolific type of what we call transient signals that vary in time, quickly, and so it's similar to short gamma ray bursts because we don't exactly know what their origins are, but we think they're connected to magnetars, which are highly magnetized neutron stars, and they're extremely prolific, and kind of looking at their origins and stuff too.
So all 3 of these kinds of things seem to have something to do with neutron stars.
Yes.
And so
that's kind of the overarching thread.
3 categories were short gamma ray bursts,
gravitational
wave events, and then fast radio bursts.
And it's kind of, I think neutron stars are cool, and I use it as motivation for trying to thread everything together. But really, I'm interested in if we have a new type of explosion or transient that we don't understand, and we can make progress by looking at other wavelengths. And I'm really excited about it.
Okay. So since neutron stars are a common thread, why don't we start by saying what is a neutron star?
Okay, a neutron star is when you have a massive star that's 8 to 10 times the mass of the sun. It undergoes stellar evolution. It explodes as a supernova, basically sheds its outer layers, and it leaves behind this compact core, this remnant called a neutron star.
So like it explodes, but the core of it it stays bound together.
That's right. Yeah. Yes.
And it's this really compact thing called a neutron star.
Yes, and it's neutron rich, but it's not necessarily all made of neutrons. In fact, like the crust is, a lot of protons and electrons, and the innermost layer, like the core of a neutron star, it's not exactly known what.
Oh yes.
What that
so
state
when
of matter
we describe
is.
it, I think the way we describe it often sounds like it's 100% neutrons,
right?
But it's very dense with neutrons.
Yes, exactly. Compared to other objects in the universe.
Right.
So So between like a regular star and a black hole, and a white dwarf, there's kind of these different states of equilibrium that you can achieve, and a neutron star is one of them. So you have a star, low mass stars end up as white dwarfs. These are carbon oxygen cores, but then the next most dense thing is a neutron star.
Right.
There's more massive stars involved in, and then the black holes, of course.
And then black holes.
Yeah.
And neutron stars are a lot more dense than white dwarfs.
Yes.
But they're getting, I guess, depending on how you define the density. I guess you could say the density of a black hole is infinity, but
but it's like six orders of magnitude, more dense than a
the neutron star,
a white dwarf. Is
about a million times more dense than a white dwarf.
Yes, that's right. Yeah, and I think it's like 1 teaspoon of neutron star stuff is like several tons or something like that. So it's really that's
I think I saw that in Frank Shu's textbook.
Yes, so I stole it.
Okay, good.
So neutron stars kind of happen to underpin a lot of the research, like in terms of fast radio bursts. Like these neutron stars can achieve very high magnetic fields. Like everything has a magnetic field, like the Earth, the Sun, etc. So we're talking about like, many, many orders of magnitude larger than the Sun's magnetic field on neutron stars, and it can emit lead to really funky processes that we think are fast radio bursts.
Right. So sorry, we jumped ahead to the magnetic fields on these neutron stars. That's fine. But that's a great way of just illustrating it. Is like the Earth has a magnetic field, the Sun has a magnetic field.
Yes.
All these massive bodies have magnetic fields associated with them, but then these really compact ones have really strong magnetic fields.
That's right. Yes.
So a neutron star can have some of the strongest magnetic fields you'll find
in the universe.
That's
right. Yeah. And then that can lead to really funky stuff happening on their surfaces.
Right.
Field lines can get twisted and reconnect. And also these neutron stars, if it wasn't enough that they're extremely dense, high magnetic fields, they can also be rapidly spinning too. So that can kind of create funky magnetic field configurations. So it's kind of like a tangled mess. And that's like a hotbed for some of these transients or explosions that we see.
Okay, and so and I should be guiding this conversation somewhat, shouldn't I? That's all right. So you're describing the neutron star magnetic field. I think that's a reasonable transition to fast radio bursts.
Yes.
So that's one of the things you work on.
Yeah, so one of the things I work on is fast radio bursts. I got into this field in 2020. There are radio facilities around the globe that are detecting these. So I kind of got invited into some of those collaborations. Really I'm interested in, like, once we know a fast radio burst occurred, going to look to see what type of galaxy it came from, and kind of charting out, okay, did it come from a region where there's lots of stars or like nothing at all, to try to get clues on like what types of, how was that magnetar created, like what, is there anything special about this progenitor?
Okay. Yeah. So when you're looking, the idea, because you look at these things observationally.
Yes.
And so you'll get data that there was this fast radio burst, or some alert, there was a fast radio burst, and you feel points in this way, and so you say, okay, what is over there?
Yes. Yeah, exactly.
You look at the galaxy and you say what type of galaxy, and that may tell you something about what
formed it. Because one really interesting result is we expect that, okay, if they came from these highly magnetized neutron stars that were born from supernovae, supernovae are from massive stars. So I'm like just kind of playing the tape back. So massive stars we know are born in very specific places in the galaxy. Like if you have ever seen like a picture of like a beautiful spiral galaxy, those kind of like dots that light up the spirals are kind of these massive star forming regions.
Okay.
So we expect that fast radio bursts come from these types of regions.
Okay.
And so that's, one of the predictions we're trying to test.
I see, because it would have there would have been some supernova not too long ago.
Yeah.
Some I don't know what not too long ago means.
Yeah,
but
like years to decades. Yeah.
And then they left behind a neutron star, and then so that region should be a place where that forms lots of massive stars in order to make that supernova happen.
Yeah. So we're kind of testing those types of predictions, like where they occur in their galaxies. Do they occur in galaxies with lots of star formation happening? That type of thing. Yeah.
Okay.
Yeah.
Cool.
So it's a very exciting field. Yeah.
And so and so then, can you give me can you give me an example of a cool result that's come out of that? Yeah.
So I think there's a couple things. One is, so I'm part of CHIME, the Canadian Hydrogen Intensity Mapping Experiment. That sounds like nothing like FRBs, but part of this intensity mapping experience is an FRB collaboration. So basically, this CHIME experiment finds 100 or so FRBs every year, even more maybe. And
just to clarify, FRB means fast radio burst.
Yeah,
that's okay. I just wanted to just for the sake of anyone that missed that.
And so, but the location was quite poor before. Like for these 100 fast radio bursts a year, it wouldn't be able to localize very well. So it would be able to say, oh, it happened like in some general region of the sky, within what we call like a few arc minutes, but not necessarily be able to be good enough to pinpoint it to the galaxy it came from.
I see.
But now actually a really exciting upcoming development is there's three like mini chimes that are being constructed or starting operations in Canada and the U.S. One is at the Green Bank Telescope site in West Virginia. And these mini chimes are going to help with the location information. So now it will enable like 100 FRBs per year, but like very, very precise locations. And so something that's really exciting is like we're sitting on like a incoming flood of fast radio bursts that are going to be localized.
Yeah. So we'll know where they came from, and you can start to learn about what sort of environments produce these things.
And then the other like science result that's come out is that there's a fast radio burst that was in so a lot of them are in these star forming regions where we expect massive stars to occur, but some of them are, but one of them was in a very old environment, globular cluster, what we call it. Like it's a very, very dense cluster of stars. And they're some of the oldest stars that we know of in the universe in these clusters. And and this fast radio burst was like pinpointed to this 9 billion year old globular cluster.
Okay.
Very much older than we'd expect if it just came from a massive star. So that's like kind of turned the field upside down.
The point is massive stars don't live that long.
Yeah, exactly.
So it couldn't be a newly born magnetar from a massive star, or something else happened that gave you this.
Yep.
Okay.
Yes, and so that's kind of turned the field upside down. Like, how do you explain that? And then the other thing about fast radio bursts is that some repeat and some do not.
Okay.
And so we don't know what causes some to repeat and some. And the repeating ones are like they can repeat like 100 times an hour. Like it's really, really active.
Wow. So in other words, like whatever neutron star is making this fast radio burst, there has some magnetic field around it, and sometimes it'll just do one outburst from I guess the magnetic field on the surface, but sometimes it'll be occasionally, like regularly, semi-regularly shooting out some kind of radiation.
And it's really irregular too. Sometimes it can be really, really active, and other times it can be like once every year or something like that. Yeah. So it's a really bizarre, interesting field. Yeah.
Oh, cool.
Yeah.
And
that was branch 1, but we don't have to talk about all of them.
That's all right. We don't have to. Yeah, we don't have to get to every single thing.
Yes.
But that's very cool. So so that's it's kind of neat because we had Maxim Ludikov talking, and so he was talking about all of the ideas behind how these things are made. But it's cool to see that there's a lot of work you could do to really say something about what caused, how they're actually caused. Like
exactly. From observations. Yeah. Mm-hmm.
Great. Maybe I should ask you a little bit, because you talked about short gamma ray. There's more other things that neutron stars do.
Yeah. And this again came from, I'm always interested in neutron stars, but came from actually my PhD advisor. I remember I signed on with him because he said there's this class of things called short gamma ray bursts. They're the most energetic explosions in our universe. We don't really know what causes them, but we have some data on their galaxies, or their home galaxies. Do you want to work on this? And I'm like, that sounds cool, like origin story, we don't know. And then throughout my PhD, I did kind of the similar things that I talked about for fast radio bursts, where I kind of looked at where they're in their galaxies, what types of galaxies they came from, and through a bunch of other different studies, we concluded that they're probably from the mergers of two neutron stars. So you have like two neutron stars, they're gravitationally bound, and over millions to billions of years, they merge in on each other on like a death spiral, and collide eventually. And when they collide, they give off this gamma ray, this short gamma ray burst.
And so how did you know that was what they were?
It's a mix. So things like, so it's a lot of what we call circumstantial evidence. So one of
nowadays that's the very well accepted thing.
Yes,
but
nowadays, and we have direct evidence now. But this was before we had any direct evidence as to their origin. So they occurred far from star-forming regions, and there's only a few things that can actually do that require. And neutron stars are one object that can kind of migrate from its birthplace, because a neutron star again is from a supernova explosion. If that supernova explosion is asymmetric, or like kind of basically pushes out material in one direction more than the other, then that can impart like a reverse, what we call kick on the neutron star.
Right.
So the neutron star ends up being kind of like flung in the opposite direction.
Okay. So the unbound material from the supernova gets a kick in one direction, and the neutron star gets a kick in the other direction.
Yeah, exactly. And so that means in practice that if you have anything involving a neutron star, you can actually like migrate away from where you were.
The neutron star doesn't have to be where it was formed.
Exactly.
It can move. It can move some distance away. Whereas other things, it's harder to make them.
Exactly. Like massive stars are kind of tubby and don't move. If there's supernova explosions, they don't move. Yeah. White dwarfs also don't really experience large kicks.
Right.
Black holes also not as significant. So.
Okay.
Yeah. So that was one thing where like, okay, they occur far from any region of star formation, and so like that has to involve neutron stars.
So you still see them in the galaxy, but just not in this. You can pinpoint that they're not in the star forming regions.
Exactly.
So they wherever they were originally formed, they moved a distance away from.
Yeah, that was the prediction. And then also that like the rates of these events, like the fact that now you have not only one neutron star but a second neutron star in orbit, gravitationally bound.
Right.
That's a difficult scenario to achieve.
How often does that happen?
How often does that happen? And those match kind of the rates of short gamma ray bursts too. So,
so those two pieces of information, you were able to reasonably.
Those were two of the main pieces of information.
You were saying those all pointed to the idea that there was a merger of two neutron stars that caused these short GRBs.
Yeah. And then in 2017 there was direct evidence.
In 2017 we know that for sure.
Yes.
Because why don't you say it?
Oh yeah, no, because we found a neutron star merger that we know occurred via what we call gravitational wave emission, and then very quickly there was a short gamma ray burst that was detected. So that literally was, there's few times in astronomy that we can in transient astronomy that we can actually really pinpoint direct evidence for the origins of a transient.
That's right. Most of it is always circumstantial, and you kind of work with the working theory.
Yes.
But there it was very direct evidence because that gravitational wave signal came directly from the mass that was spinning around. Create this pair of neutron stars distorting space-time. And we could compute how much mass there was there.
Exactly.
And so we knew that they were neutron stars. They weren't something
else.
else.
Yeah.
And so other things can't do that.
Yeah.
And so we knew that. So just from the gravitational waves, we knew it was a pair of neutron stars.
Yes.
And then also right after that, there was a short gamma ray burst.
Yep.
So we're like, okay, that's what that.
Yeah, that's what that is.
How much more evidence do you need?
Exactly. Yeah. So now, like, going forward, really like interested in following more of these gravitational wave events and looking for other, signals too, as well. So yeah.
Very cool.
Yeah.
Excellent. So that's so I should say we didn't really say what a gamma ray burst is, but that's okay. It's a burst of gamma rays.
Yeah, it's a burst of gamma rays. It's the highest energy form of light that we can detect.
Right.
Yeah. Yes.
Okay, great. And so now those are some great examples. So now what are you interested in working on in the future?
Yeah, so I did mention these like mini CHIME telescopes, so that's really going to provide a flood of new fast radio bursts and really getting into kind of large populations of fast radio bursts, where they come from, to try to like see how prevalent different kind of rarer populations are. Like, are there some that, like, how many actually form in these globular clusters? That's kind of weird, versus others. Is there anything different about the population of fast radio bursts that repeat versus don't?
Yeah.
Can we see that distinction in the environments? And that can only be done with like a large sample.
Right.
So on that front, and then neutron star mergers. I think we're just waiting for the next one. So
yes,
yeah,
of course, for sure.
Yes.
I'm curious then. So you think these repeating ones you think that they may be in different environments than the non-repeaters?
We have no evidence to say that they definitely occur in different environments, but there's some trends. We think they occur in overall like smaller galaxies that are more actively forming stars. Okay. And so than the ones that don't repeat. So we think maybe these repeating fast radio bursts, they're all magnetars, but the repeating fast radio bursts are just younger magnetars that have higher magnetic fields and basically repeat more. Okay. And then the ones that don't repeat, these non-repeating ones, are just older,
and then maybe
tired.
They're shooting out a fast radio burst once every 100 years or something.
Exactly. So we wouldn't be sensitive to.
Right.
Yeah. So that's the working possible theory, but we should see that also imprinted on the galaxies that we see them from. Yeah.
That's very cool.
Yeah.
All right. Now I'm going to ask the question I ask everybody.
Okay.
Which is, in your opinion, why should we care about astrophysics?
Yeah. It just like tugs on your intrinsic curiosity. I mean, I think astrophysics, no knock on other fields, but like we try to answer extremely big questions about the universe, like fundamental questions, like how did we get here? What is the universe expanding? What is our place in the universe? I think that's really, like, these are just really ambitious, big picture questions that I think everybody should be kind of excited about. And then of course we're all interested in like the little details and stuff, but and then interact like in terms of what I do, like this interacting with the universe in a way that's kind of on like a human time scale. Like one day you see an explosion, the next day you go chase it, and another day you see a new explosion, and it's like kind of a dialogue with the universe. It's really like beautiful. So
that's a great answer.
Yeah.
All right, well, I think that's all I have to ask.
Okay.
So thank you so much to Dr. Fong for joining us. I had a lot of fun talking science with you.
Yeah, that was really fun.
And I hope you'll join me again sometime.
Yes. Yeah. I'll be back.
All right. Thank you.
Bye.
Nice that I got a chance to catch up with Wen-Fai. I really hope that she's willing to come back, since I feel like we only just scratched the surface of her research. So thank you again to Dr. Fong, and thank you to our listeners. We will see you next time. The Astrophysics Podcast is currently unfunded. Right now I'm doing just for fun, but always ad-free. All the music you hear on the Astrophysics Podcast was written and recorded by Britton Ashford, and you can find it on her album Trotter. All songs are used with permission from the artist and producer. Look her up if you enjoyed the music. This podcast is produced in beautiful Lafayette, Indiana by me, Paul Duffel, Professor of Physics and Astronomy at Purdue University.